Hey everybody, we're doing IIT JEE 2023 paper 1 problems. Some of them problems are very good actually, and some really silly. We're on to section 3, and this is the fourth problem in section 3, which is just so you get a positive integer as an answer. And you get a full credit if you get the right answer, and you get a 0 if you get a wrong answer. So there's no partial credit, okay? Alright, so this is a question that if you look at it closely, a closed container contains a homogeneous mixture of 2 moles of an ideal monatomic gas. So if 2 moles is a homogeneous mixture of 2 moles of one gas and 1 mole of another gas, and they differ by degrees of freedom because the gamma is 5/3 here and gamma is 7/5 here. It's like it's monatomic gas, like like something that's only one atom, like a helium, one atom per molecule. It's like a helium gas. And this rhodomatic gas will be like a hydrogen, molecular hydrogen gas or molecular oxygen gas. They don't give you the mass and they don't give the identity of the gas. It's just 2 different kinds of gas with different degrees of freedoms, where if the gas has a certain internal energy, you can how many ways the internal energy can be accounted for. Okay, here gamma is the ratio of the specific heats at constant pressure and constant volume of an ideal gas, CV and C. So you already know like gamma is Cp over Cv. Alright, the gas mixture does a work of 66 joules. So when heated at constant pressure, the change in internal energy is this. So it says that you have the gas and when heated at constant pressure, so it used to be over here, and then it goes to some volume here. The pressure is same, so the Pi is some P, and P final is Pi, same P, and throughout this is constant pressure. So if you do PV diagram, it's so some Pi. So that's the initial and this is the final, the initial volume, and this is final volume, and nothing else is given. Okay, and you're supposed to find given the work, this is given, this area under this curve is given to be 66 joules, and so find U final minus U initial. Okay, I'll let you kind of think about it and with this description and maybe try to do it. I hope you made some progress in solving this problem. So a couple of things you have to know about the ideal gas is so it is mixture, right? But the ideal gas, they don't interact with each other, so you can think of them as each contribution coming from the separate gases, right? So if I have one gas, then in the ideal gas at temperature T, its internal energy is simply U equals to degrees of freedom for each molecule, number of moles over 2. For each degree of freedom you're gonna have RT, and so and PV equals to nRT can be used to write this guy as df/2 PV for the ideal gas. So you can see for each ideal gas, right? So what do we have here? If you have a mixture, then U will be degree of freedom of the 1 plus how many moles you have R T. You can see both of them have to have same temperature, and then you're gonna have df of 2 N2 over 2 RT. So basically it just turns out to be you have a df1 N1 per df2 degrees of freedom. Let's call it subscript a little bit, df2 N2 half RT. How about when expanding on this? So at this point is like a T final, this is temperature initial. So if I look at this UF minus UI, what are we going to have? We're going to have let's call it D1 N1 plus D2 N2 times half R T final minus same stuff T initial. So how about the work done? And the work done I to F is the area under this thing, and it's just a common pressure P V final minus excuse me V initial. So this is a PV finals minus PV initial. So it's just going to be so if you write this down, so this just turns out to be this N now net amount of gas there is, net nRT final minus nRT initial, with N simply equals to 2 types of gap you have. It's total here. So if I look at it here, then what we have N1 plus N2 times R TF minus TI, and this is given, right? So I can see the R times this is just W over that. So R times TF minus TI is simply work done N1 plus N2. Now I can plug in there to get U2 minus U final minus U initial. That's the one we're supposed to figure out. And you can see over here you have a D1 N1 plus D2 N2 over 2 times RTF minus TI, and for that I can use this. So this whole thing can come down here, WI to F over N1 plus N2, and now everything else is known here. To get D1, gamma is 5/3, that corresponds to D1 equals to 3, and gamma equals to 7/5, so D1 equals to 5. Okay, so we just plug in here. We have a 3, N1 has a 2 moles plus 5 times 1 mole over 2 times amount of work is 66. This is joules, and N1 is 2 plus 1. So what do we have? This cancel, that's 33, and 6 plus 5 is this makes it 11. 6 5 is 11. So I get 121 joules. Okay, so this is a interesting problem. You can see that this problem, if you go, a couple of things that we have to actually know. We have to know that we can get degrees of freedom from the gamma values that are associated. And so what happened when, okay, let's just look at gamma equals to 5/3. Why do I give you D equals to 3? Okay, so this one, this is of a CP over CV, and CP is CV plus R and CV. So the CV is the number of degrees freedom times R, and number of degrees freedom times R plus R. So if you work it out, so it's a 3/2. So let's say so dF plus 1 over dF equals to 5/3. So actually I think I've kind of messed up here. You have to add 2 here because of, so yes, 2R. Okay, so from here you can see that dF 3dF plus 6 equals 5dF, so dF equals to 3. So when gamma equals to 7, I think it was 7/5, yeah, 7/5, then this will be equal to dF plus 2 over dF, and that just will give me 7dF 5dF plus 10, so dF equals to 5. So that's how you can get the dFs, and everything else is kind of like follows pretty standard ideal gas. Another thing I can think about is this formula, that actually these two formulas are kind of important. This formula here is important to remember, because ideal gas, the internal energy only depends on the temperature, and that sometimes gets tested in other situations. Okay, so I'm going to stop here, and I'm going to do another problem, the next problem in this section, in another video.